Alright, so I want to talk about the chain rule. So chain rule. So the basic idea behind the chain rule is if I take the derivative of some function raised to a power, then I can sort of apply the power rule to it, except then I need to multiply by the derivative of the function. So for example, the derivative of the natural logarithm of x to the third is 3 times the natural logarithm of x to the second power times 1 over x. And if I have the derivative of e raised to the power of a function, then I'm going to get e raised to the power of the function because the derivative of e to the x is itself, but then I'm going to multiply by the derivative of the function. So for example, the derivative of e to the x squared plus 3x minus 4 is e to the x squared plus 3x minus 4 times 2x plus 3. And lastly, the derivative with respect to x of the natural logarithm of a function is 1 over the function times the derivative of the function. So, as an example of that, the natural logarithm of, let's say, x squared minus 5, if I take its derivative, is going to be x squared minus 5 in the denominator, and the numerator is 2x. So the usual way of comparing these is the power rule says the derivative of x to the n is n times x to the n minus 1. So you can think of this as the extended power rule. If you take the derivative with respect to x of something that's called u to the n, you get n times u to the n minus 1, but then you multiply by the derivative of u. And the derivative with respect to x of e to the x is e to the x. So that means the derivative with respect to the x, with respect to x of e to the u, is e to the u times the derivative of u. And the derivative with respect to x of the natural logarithm of x is 1 over x. So the derivative with respect to x of the natural logarithm of u is 1 over u times the derivative of u. So the general way of thinking about this is you talk about what's called function composition. So the idea is, suppose that f of x is the function square root of x, and let's say that g of x is the function e to the x plus 5. Then f of g of x, with a little circle there, is the function you get if you take g of x and you plug it in to f of x. Since f of x is the square root, that means you just take the square root of whatever g of x is. So in other words, f of g of x is the square root of e to the x plus 5. And so what the chain rule formally says is that if I've got two functions f and g, and I take the function composition, and I take the derivative, what you get is you take the derivative of f, which I'm going to call the outer function, you plug g into it, and then you multiply that by the derivative of g. So here is a way to think about that. Over here, this example over here, so f of x is x to the 1/2. So f prime of x is 1/2 x to the negative 1/2, which can be rewritten as 1 over 2 root x, which we've done a few times. G of x is e to the x plus 5, so g prime of x is simply e to the x. So that means that if I want to take the derivative here, the derivative of f of g is 1/2 times e to the x plus 5 to the negative 1/2 times e to the x. I'm taking the expression for g, I'm plugging it into the expression for f prime, and then I'm multiplying it by g prime. And you can rewrite that as e to the x over 2 square root of e to the x plus 5. And so if I want to think about this in the other way, what I had here was my function was e to the x plus 5 to the 1/2, and I took its derivative, so I can use that extended power rule. You get 1/2 e to the x plus 5 to the negative 1/2, and then you multiply by e to the x. Alright, so let's try this. Suppose I've got the derivative with respect to x of 5x squared minus 4x plus 3 to the 5th. Well, the outer function is this u to the 5th thing, where u is 5x squared minus 4x plus 3. So what I ought to get is 5 times u to the 4th times the derivative of u with respect to x. The derivative of u with respect to x is 10x minus 4. So this works out to 5 times 5x squared minus 4x plus 3 to the 4th times 10x minus 4. Alright, now what about if I take the derivative with respect to x of e to the 7x minus 9? Well, so I can think of this as the derivative of e to the u, where u is 7x minus 9, so I should get e to the u times du dx. So du dx is 7, so then e to the u is e to the 7x minus 9, and then you take the whole thing and you multiply it by 7. And I can rewrite that as 7 times e to the 7x minus 9. What about the derivative with respect to x of the natural logarithm of e to the x minus 5? So again, I think of this as the natural logarithm of u. So its derivative is going to be 1 over u times du dx, where u is e to the x minus 5, so the derivative of u is simply e to the x. So then this becomes 1 over e to the x minus 5 times e to the x, which I can rewrite as e to the x over e to the x minus 5. So the only way this can become worse is if the expression is more complicated. What if I ask you to do e to the square root of x minus 5? Alright? So if I take the derivative of this, then this is the derivative of e to the u, which is just going to be e to the u times the derivative of u with respect to x. Alright? So that's the e to the u is e to the square root of x minus 5. But then I need to multiply that by the derivative with respect to x of the square root of x minus 5. And then this has to also be done using the chain rule. So, so actually we'll just continue it this way. So think of this as the derivative with respect to x of the square root of u, where u is x minus 5. So the derivative of the square root of x minus u is 1 over 2 root u times du dx, and du dx is simply 1. So what you're going to get here is e to the square root of x minus 5 times 1 over 2 times the square root of x minus 5, since that's what u is in this second iteration. And so this whole thing just becomes e to the square root of x minus 5 over 2 root x minus 5. All right? So here, this is this one, and I'm going to post another video with just another couple examples worked.